Now in this section we'll look at what are called partitions of sets, and a partition of a set X ultimately divides a set X up into non-overlapping subsets. So if we look at that graphically, what we're really looking at is if we have a whole bunch of different elements across our set here, a partition would be a dividing line. It's something that we draw in to split our area, our set. And so in this case, if these elements were part of our set X, we've now divided X into what we could call an X sub 1 and an X sub 2. And those are our different partitions. Now, you'll notice that there's no elements in common between them. They are non-overlapping. And this is easy to see graphically, but mathematically we need to establish some rules to make sure that we keep everything in order. And the first rule that we'll look at is that the subsets of a partition may not be empty. So in this case, I could not have, if we looked at another example here, where I have elements like so, I could not have a partition like this, because in this case my X sub 1 is fine, but X sub 2 has no elements in it. It's an empty set, and that would violate this first rule, which is that the subsets of a partition may not be empty. Now, the second rule is really hard to see graphically, but ultimately it says that every element must be in one and only one subset. So if I take this element right here, for instance, that cannot be in both X sub 1 and X sub 2. I have to pick one of those subsets, and that's the only one it can be in. Now, the other side of this is that every element must be in one and only one subset. So to look at another example, if I draw out a set here that contains 3 elements, and I, let's say, draw 2 lines this time, I can have x1 and x2, and if all of this area here is x, then what I'm left with is an x sub 1 and x sub 2, but then this element is in no man's land. It's not part of any subsets that I've identified. So in order for this to be complete, I would also have to identify an x sub 3 to contain that element. Now, if we wanted to look at some mathematical examples, let's say we have a set S, and that S is equal to 1, 2, 3, and 4. And our goal is to create some different partitions of this set S. So the first one that we may try, and we'll do some that are invalid first just to reinforce those rules, but let's say that we have a set X, and that set X is equal to the set 1. So that's our first subset. And then the set 2. And then the set 3. And then an empty set. Well, we've actually violated at least one rule here, which is that we have an empty set, right? We violated rule 1. So this subset, or this partition of subsets, would not be valid because we violated rule number 1. We have an empty subset. So let's try a different one. Let's say that we have a y equal to 1, 2, and 3. Just get rid of that empty subset. Well, this is also invalid because if you look back at our S, we have a 1, a 2, a 3, and a 4, but there is no 4 in Y. And so Y is also not a valid partition. Now, another example we might look at is Z. And let's say that Z is equal to 1, 2, 3 and 4 as their own subset, and then also a 4. Now, in this case, we've also violated rule number 2. We have a 4 in 2 different subsets, and that is not allowed. So again, we've violated that second rule that every element must be in one and only one subset. So now that we've spent some time looking at invalid partitions, let's look at some valid partitions, because there are multiple valid partitions for this set S. And the first partition that we'll look at we'll call A. And we'll say that A is equal to the first subset containing 1 and 2, and the second subset containing 3 and 4. And this is a valid subset because we have our 1 accounted for, our 2 accounted for, our 3 accounted for, and our 4 accounted for. We have no empty sets, and we also have no overlap between the subsets in this partition. Another example we'll call B, and let's say that B is equal to 1, 2, and 4. And then we have another subset that is just 3 on its own. And this is also a valid subset. As you'll notice, we have, again, our 1, 2, 3, and 4 accounted for. They are only showing up once, and we have no empty subsets. And then a third and final example we'll look at we'll call C. And C is just going to be equal to 1, 2, 3, and 4. And you may look at this and say, wait, that's just the same set. And I would say, yeah, you're right. Because there is no rule that says that a partition cannot contain all of the elements, or that a partition has to be a subset of the elements of the set that it is dividing. So in this case, we only have one subset in our partition, but that's totally okay. This is a valid partition. Now, to put a definition of this, we say that a partition P of a set S is a collection of non-empty subsets of that set S, such that every element of S is in exactly one of the subsets in P. Now, one of the notes here that you'll find kind of interesting is that this is the subsets in P, not the subsets of P. These are ultimately subsets of the set S, but they are in P.